1, the test set for data 1, and around 0.6 for data 3. So yeah, there was a very big performance drop. So yeah, so now we can try to figure out what was the reason that was causing this issue. So now we please open the 2-0-data exploration.ipynb. So in this notebook, we are going to conduct a brief data exploration to understand the distributions of data 1 and data 3. The goal is try to understand what was the difference between these two data sets. So there are a lot of reasons that can cause the generalization gap of the deep learning model. And the distribution shift is one of the most frequent factors that we see that contribute to the generalization gap observed in our research. So what is a distribution shift? It means that if the distribution of the test data is very different from your training data set, so that the model cannot generalize what it learns from data 1 to data 3. So yeah, in this notebook, we are going to conduct a brief exploration of the data distributions across our data sets. So yeah, we want to know what are the characteristics of data 1 and data 2. And then also we want to see what caused the generalization gap. Yeah, so first we import our the package that we needed, not that we need, and we load. So yeah, we haven't taken a look at the data 1 to 3.csv. So now we are going to take a look at those information. So first, we will load the data1.csv in this cell. So in this, after we load the CSV file, we will get the data frame like this. So it contains multiple columns. It includes the information about the patients as well as the labels. So for the information about the patients, we have a session number -anon, which is the de-identified study ID, and MP_anon is the de-identified patient ID. So we also have the path, which is the path that for the images. Yeah, and also we have demographics, including patient sex, race, and age. So yeah, there are some redundant columns, such as imaging view frontal. It indicates if the image is a frontal image or not. But since we have all of our images are frontal images, so this column is not going to provide any useful information. So, and then we will define functions for our data exploration. There are 3 here. I'm not going to get into detail, but the first one is counting the occurrence of the categorical variables in the data frame. And the categorical variables are the patient sex, race, and the label for pneumothorax, no finding, and support devices. Yeah, and one thing I forgot to mention is that the presence of support device is not considered as a finding. So that means there can be overlap between the no finding labels and the support device. Okay, so the next function is to plot a bar chart for the occurrence of those categorical variables. And the third functions is the one that we use to plot the distribution of the continuous variables. But in our case, age is the only continuous variable in our data set. So we can quickly run, let me run this cell. So we can run this cell. We'll get the occurrence of the categorical variables. So we can see that, oh, let me run the second one. So the first cell is showing the occurrence, but it's stored in a dictionary. But we can use this dictionary to make the bar chart of those numbers. So we can just look at the bar charts. We can see that we have equal amount of female and male in our data set, and equal amount of black and white. So, and for the labels, we have 50% of positive pneumothorax and 50% of pneumothorax negative. Yeah, so same for support devices and no finding. So we observed that we have a very balanced data set in terms of these variables. And then we can also plot the distribution of the age. So it will generate a histogram, and it will also show the mean of the age and also the standard deviation. So we can see that the mean age was 50 years old, and with standard deviation of 16.79 here.
Yeah, so those are the distributions for data one. That's a data set you get a pretty high performance.
Mm-hmm.
Yeah. So any guesses why the model performed poor in the data set 3?
Yeah.
Maybe data unbalanced, right? So we'll see what's the distribution in data set 3.
Yeah. So let's move on to data 3. So it's basically the same as the data set 1. We generate the bar chart for the categorical variables. And also we can plot the histogram of the age. So a question, what is the difference between data 1 and data 3? Yeah, can anyone, does anyone have any thoughts? And what is causing the gap in terms of performance? Yep, that's correct. The sample size is smaller, but yeah, any other thoughts?
The question is, will sample size influence the performance? Because we didn't use the data 3 for training, right? We only use it for testing. So will sample size lead us to the performance drop?
No.
So I think the only factor that sample size can affect the performance is that the data set is not representative enough to represent our training data set. So yeah, so we can also observe that it's kind of slightly unbalanced in the categorical variables. You can see that, for example, in sex, we have less amount of males. So this may be also a reason that we observe the gap. So, but it's not that unbalanced, because from yesterday's lectures, we know that the unbalanced data set is defined as 5%. So, but in our case, we have like around 40 for male. So it's kind of still a fair, balanced data. And for age, we also observe similar mean and standard deviation. So why there is a generalization gap? So does anyone has any thought? Okay, so yeah, you already see the answer here. so, so there is another distribution that people usually miss is the label correlation. So to measure the label correlation, we need to use a metric called co-occurrence matrix. Yeah. So it's important to know that the labels are not independent. So there can be multiple findings that coexist in the image, so that they can kind of create some confounding effect to the model. So yeah, here we are going to plot our co-occurrence matrix. So we define functions to plot it. So that's what this cell is doing. So let me run the co-occurrence matrix here. So how do we read the co-occurrence matrix? So we read it row by row. So basically, it's giving us the conditional probability of one coexist findings or labels given a particular finding. So yeah, for example, let's read the first row, which is the pneumothorax. So the upper left numbers is saying that given the presence of pneumothorax, the probability of having pneumothorax is 1. Yeah, so it's very straightforward. But the second one is telling us that given the presence of pneumothorax, the presence of support devices is 1. That means all the pneumothorax images has support devices. So yeah, let's see the third row. And the third row and the second cell, the second values here. Yeah, can anyone tell me what it is telling us? Yes, so it's saying that given the presence of no finding, the probability of support device is 0. So when the image has no finding, there is not going to be the support device present in the image. So, but yeah, just a review. So no finding, and so support device is not a finding, so they can co-occur in one image. So now we know how to read the co-occurrence matrix. We can run the next one to see what is the co-occurrence matrix for data 3. Okay, so can anyone tell me what this metric is telling us? Yeah, exactly. And there is one more, this one. So this the third row, no finding row, this number. So it's telling us, given the presence of no finding, the probability of getting support devices is 100%. So it's kind of the total opposite scenario with the data 1. So this is very likely to be the reason that we are experiencing generalization gap. Sorry? So support device or something, some devices used in the ICU. Yeah, I think Harry or Judy can explain this better. But in our case, it's mostly chest tubes. Yeah.
Yeah, so support devices is any device to support the life of the patient. So that would be a chest tube, a central line. Sometimes could be considered pacemakers, like for permanently implanted devices, but they're basically very big and radio dense often, so they can be big confounders.
So chest tube are used to treat pneumothorax, so that's why they co-occurred frequently. So, yeah. So let's move on. So remember, we have another data set 2. So now we can see what's the distribution of data 2. So it has the same distribution in terms of the categorical variables. It's a well-balanced data set. And for the age, we also see similar mean and standard deviations. But now something is different. So in this matrix, we observe that given the presence of pneumothorax, there is 50% of probability that the image is also having support devices. And on the other hand, for no finding cases, we also set it as 50% for support devices. So in this way, we kind of remove the correlation, label the correlation between the pneumothorax and support devices. So in the next notebook, we are going to train the model again to see.
Yeah, so now you see there are co-occurrence between pneumothorax and support device. But why does it lead to the performance drop? Anyone have no?
Exactly.
I will prefer to use the shortcut to explain this phenomenon. My question would be, what do you think? Which test is easier for machine? Detecting support device or detect pneumothorax? Which one is easier? Support device, right? So our machine is quite smart. They will choose the easier way to get a higher performance. Right? So instead of to detect the real features of pneumothorax, they prefer to detect the support device because that's an easier job for them.
Okay, so yeah, let's go ahead and train the second model using data 2. Yeah, and this is almost the same as the training of using data set 1. So I think we'll leave 10 minutes for everyone to train the model. In the meantime, if you have any question, we can help. Yes. Yeah. So Xrays X-rays are information-rich images. So usually there are a lot of findings in one image. It's not as simple as what we shown here, because what we shown here is it's a toy data set that we make it for educational purpose. So during the data zone, you will get a chance to use the whole MRI checks X-ray, and you will see there are a lot of confounding factors, noises in the real data set.
And just for clarification, right now for the next 10 minutes, you're just going through 2.0 and 2.1, which is a repetition of the earlier ones, but there's a catch that will be summarized at the end. And then we, just based on feedback, again, as we've encouraged as you go along to help us make this good for you, Professor Moning has agreed to give a 30-minute talk that is going to be a little bit of a primer for very, very basic introduction to what's a convolution network, so that all the work that Frank and Pochi did is going to again solidify, and that's going to be important moving forward. Go.
So it's installed in the FSX, so you have to copy it. Oh, not this one, sorry. Oh, this. Just copy the data. Click, there's a square icon here, and you can shut down all the kernels for each notebook, and then run the current notebook again. Okay. Yeah. So the reason is that you will only have one GPU to run the code. But if the GPU has been allocated to a certain notebook, then you won't be able to use the same GPU for the other notebook. Okay. So that's why you have to shut down all the kernels. Okay, I think we should move on. So I'm going to wrap this session up. So I'm going to run the last notebook, which is 3_summary.ipynb. So in this notebook, we are going to compare the performance side by side for the model trained on data 1 and model trained on data 2. So I'm going to call it model 1 and model 2 in the future. So you can just run the code. It's basically aggregating the results from your evaluation. So from your evaluation, the code is saving your result in the result folder. Okay, let me. I don't know why the kernel is not connecting to our notebook, but it's fine. I already have all the results like plotted here. So if you run the code here, it will aggregate the results for you. So you'll generate the confusion matrix for model 1 and model 2. You can, so the figures here is showing the performance of when evaluating the performance on the internal test set, which is a subset of data 1 and data 2. So we observe like they reach very similar performance in the test data set. So we can do the same for the external data set. We just run the code, and then it will show you the confusion matrix of external validation. We can see that model 1 experienced a large performance drop, but model 2 kind of preserved the performance in the test data set. To make this more clear, we can calculate all the metrics that Pochi introduced. Yeah, so this code, you don't need to worry about them too much because they are just aggregating the results from the file. So if you get it here, you will see all the metrics for model 1 and model 2 side by side. So you can easily compare the difference between two models. Yeah, so can look at AUC. You can see that the model 2 did not experience a performance drop, even increased a little bit, but yeah, I would say it's pretty similar. So that means the model trained on data without any shortcut can better generalize to the external data set. Okay, so just a quick summary of this session. So in this session, we learned the fundamentals of training a deep learning model, including the imaging loading, hyperparameter tuning, and also monitoring and interpreting the training curve, the loss curve. And we also did the model evaluation on the internal test set and also external data set. So we also learned about how the label correlations or shortcut can impact the model's generalizability. So I hope in this session you will be able to build your own model in the future and also understand it is very complex in medical imaging AI. There are a lot of confounding factors, noises in the real world scenario. Yeah, I think that's it. Thank you.